Something weird is going on here. I have a transparent piece of plastic. I can move it up and down in front of the camera and nothing much happens. But if I flip it over, suddenly the square gets darker, but only when I move it in front of the camera. Now it's not just that the light's going through the film twice when it's in front of the camera, because when it's flipped over, it doesn't look darker. It's almost like this plastic is a one-way valve for light. And why does it only get darker when it's in front of the camera? What is going on here? So let's see if you can understand how this mirror demonstration was working by the end of this video. If you can't, then at the end I'll tell you how it worked. In this video, I'm going to show you how all light comes in only two flavors, left-handed spin and right-handed spin, and how this spin affects matter, and how a slight imbalance in one versus the other led to the evolution of chiral molecules and life itself. But before we continue, I want to thank the sponsor for this video, Helix Sleep. Did you know that you spend about a third of your life in bed? So it makes no sense to settle for a mattress that isn't built for you. What I love about Helix is that you don't have to guess which mattress you'll like. You just take their quick sleep quiz online and answer questions about how you sleep, your body type, and what you need support-wise. And then they match you to the right mattress. I was matched with the Helix Dusk Luxe, and switching to it was a huge upgrade from my old mattress. I sleep deeper, I wake up less sore, and I'm not overheating at night anymore, which was a huge problem for me. Especially in the winter when we're spending more time indoors and in bed, having the right foundation for sleep really matters for your health and energy. Another thing I love is how easy the whole process is. It ships straight to your door, sets up easily, and comes with a 120-night sleep trial and a lifetime warranty, so there's zero pressure. And one more thing I want to mention. If you're not ready to replace your entire mattress yet, Helix also makes mattress toppers, which honestly is a really smart option. They let you update how your bed feels without starting from scratch. So I went ahead and tried the Luxury Plush Premium Mattress Topper. And what I like about it is that it adds comfort and support right where you need it. It's great if you're trying to extend the life of an older mattress or just fix up a guest bed or fine-tune your sleep setup. And because it's Helix, it's still designed around real sleep needs like pressure relief, alignment, and even sleeping cooler. So whether you're ready for a full mattress or just want a noticeable upgrade, the topper gives you a really flexible way to improve your sleep. So if you want to try out Helix, right now they're running a flash sale exclusive partner offer. So you can go to helixsleep.com/actionlab or scan the QR code on screen. And then you just take the sleep quiz and you can get 27% off site-wide. So a huge thanks to Helix Sleep for sponsoring this video and upgrading my sleep. But now let's get back to our experiment. Any photon of light that exists, no matter the color or wavelength or anything about it, exists as one of two flavors that we call spin. It can have a +1 spin or a -1 spin. We also call this polarization. If you think of a photon as a wave, then this means that the electromagnetic wave is either spinning clockwise or counterclockwise as it moves through space. But light doesn't always act like waves. Sometimes it behaves like individual point-like particles called photons. And each individual photon also still has this polarization. So how can a single photon have spin though? Does that mean each photon is like a tiny spinning ball? Well, the answer to this is no. And to understand why, we have to rethink what spinning actually means. Imagine a perfectly smooth sphere with no markings at all. If I rotate it, there's no way to tell. But if the sphere is actually spinning, then when we try to twist it, it resists rotation differently depending on the direction that we try to twist it. If it isn't spinning, it feels the same no matter how we rotate it. For example, if you hold a fidget spinner, even without looking, you can tell if it's spinning or not just by twisting it, because you can feel the gyroscopic resistance. This tells us something important. Spin isn't necessarily about motion, it's about symmetry. There's this fundamental rule in physics called rotational invariance. It means the laws of physics don't care how you orient an experiment. For example, if you perform an experiment and then rotate the entire setup, the sources, the detectors, the objects, everything, the outcome stays the same. This rule cannot be broken. Now here's the important consequence of that rule. If something appears to behave differently depending on its orientation, then that difference cannot exist in isolation. The only way rotational symmetry can hold is if the object transfers that directional preference to something else. That accounting is what we call angular momentum. So that means if something is not symmetric under rotation, if rotating it actually changes its state, then it carries angular momentum. So that's what we mean when we say that photons have spin. Their quantum states, especially their phase and polarization, aren't symmetric under rotation. If you rotate space, the photon state changes. And whenever rotation changes the experiment, angular momentum must exist. So photons have intrinsic angular momentum even though nothing is physically spinning. This might sound familiar because electrons also have spin. Electrons aren't spinning little balls either, but their quantum states also change under rotation. So they have intrinsic angular momentum as well. So much so that if you're somehow able to flip electrons over, like in this experiment I did earlier, it causes your whole system to spin due to angular momentum changes. So all light comes in either a left or right spin or polarization, and it's exactly a 50% mixture. So that's why when I just look through a right-handed circular polarizer, exactly 50% of the light gets blocked no matter how I change the polarizer. Exactly what you'd expect. But something weird happens if the light passes through something that was made by living things. This is sugar made by plants, specifically D-glucose. Now, because of the shape of this glucose, the speed at which left and right spin light travels through it is slightly different. This creates a really interesting effect, where it will rotate light that's in a superposition of both left and right-hand polarization. We just call this linear polarization. So if I pass this linearly polarized light through this long column of sugar water, then run it through another linear polarizer, we can see that the polarization of the light has changed angles, so that when the screen is dark, the glucose mixture is light, and vice versa. Now, I'm only using one color of light here because if you use white light, then you kind of get a rainbow effect and it's harder to see. So the reason that this happens is that all of the molecules of glucose were made in one specific way. They have a certain handedness to them as well. Chemically speaking, sugar could be made like this, but also the mirror image of this as well. But in nature, we never find it like this. In labs, we find the left-hand and right-handed mixtures in the exact same quantity, but in nature, that's not so. And this is true not just for sugar, but for amino acids as well. They can be made by both the right-handed version or the left-handed version, but in our bodies and in all of nature, they are only found in one way. It's as though the ability to absorb a specific spin or polarization of light based on its structure is baked into how it's made. But if light is a perfect 50-50 mixture of left and right-handed light, why would life evolve with an uneven mixture of these left and right-handed molecules? Well, scientists recently discovered a clue about what broke this initial symmetry. In regions where stars are forming, dust clouds can scatter starlight in a way that produces circularly polarized light, light that twists predominantly left-handed or right-handed instead of being a perfect 50-50 mix. Laboratory experiments show that when chiral molecules are exposed to even a small excess of one handedness of circularly polarized ultraviolet light, one mirror form is destroyed or altered slightly faster than the other, creating a real imbalance. So over thousands of years, that tiny bias would be enough to imprint a preferred handedness into organic molecules forming on interstellar dust grains. Those molecules could then be delivered to the Earth by meteorites and comets, already tipped toward one-handed form, providing the initial asymmetry that biology later amplified into the all left-handed amino acids. What's crazy about this is that the tipping of the scale to favor one-handedness versus another is exactly what's necessary for complex life to form at all. Because if biology were built from an even 50-50 mix of left and right-handed molecules, the chemistry of life would grind to a halt. Proteins would no longer fold into precise, repeatable shapes, and enzymes wouldn't lock into their targets. And DNA couldn't form stable, uniform helixes. So we should be thankful for the fact that light has spin and that the Earth was in a place where it wasn't exposed to exactly an equal amount of each. So now that we understand polarized light, let's explain what was actually happening in their mirror experiment at the beginning. That plastic sheet is a circular polarizer. It only lets through one spin of light, say right-handed. So when you look through it normally, unpolarized light from the room hits the sheet. Half gets through and everything looks transparent. But when you move it in front of the camera and look at its reflection, the light passes through the polarizer again. The first pass selects only one spin, and that light reflects off the mirror. And here's the key part. The reflection then flips the handedness of circularly polarized light. When that flipped light comes back through the polarizer, the sheet now blocks it completely. So in the mirror, it suddenly looks black. Now what about when we flip the sheet around? Well, in that case, the effect just disappears. That's because circular polarizers only work in one direction. They're made by layering a quarter wave plate together with a linear polarizer in that specific order. If you use it backwards, it no longer acts like a circular polarizer. It just behaves like a linear polarizer. And linear polarization doesn't flip its orientation when reflected off a mirror. So the light isn't canceled on the second pass. And thanks for watching another episode of the Action Lab. I hope you learned something. If you haven't subscribed to my channel yet, remember to hit that subscribe button, and we'll see you next time.